Oh, okay. One moment.
Yes, I think I'm recording. Yeah, I'm recording. Ben, you can go.
Sure. Can you see my screen, Peter?
Yep.
Awesome.
I just saw
Okay.
like a big version of my face on your screen. Now I see the paper.
Perfect. Okay, now can you see the paper?
Yep.
Okay. Okay, hi. Ben here. Welcome to Paper Club. Hopefully this will be 40 to 50 minutes of relaxed discussion about graph machine learning. Because I'm quite new to the graph machine learning literature, by no means an expert. So hopefully we can learn a bit together about the types of applications that graph machine learning encompasses, and also the types of fundamental challenges involved with graph machine learning. I'm sure there's plenty of ideas in the room if we can bring them out by discussion, because you guys will know a lot about graphs. And I chose this paper because I hope it can point out some of the challenges in graph machine learning, particularly because there's quite a bit of disagreement in the title, because graphs work in discrete state spaces, right? At least adjacency matrices do. There's an edge or there isn't an edge unless you have a weighted adjacency matrix. Whereas diffusion models work in fixed dimensional continuous state spaces. So that's continuous, not discrete, and fixed dimensions, so a fixed number of pixels or a fixed state space rather than a number of nodes that can be kind of any number. So that disagreement or discord might be the source of some discussion. So generative, can anyone tell me what generative means? Well,
You know, I feel like it's a term that has too many definitions.
overly loaded term. So generative.
Here, I feel like generative means like a sampling model.
Yeah,
but
sampling models usually take like a latent variable and push it through a decoder and generate some state variables. So going from like noise to data is a typical phrase. In the context of graphs, what might the state variables be? Well, there could be node features. They could be edges, so link prediction. It could be all of nodes, edges, and node features, so generating a whole graph. But that seems like quite a challenging application because there are not many papers that are discussed within this review paper that talk about generating a whole graph. And that's the other point to make. This is a review paper. So it's kind of pointing to different parts of literature, bringing together different parts of the literature. You can see in figure 1 some methods that exist elsewhere, apart from diffusion models, so normalizing flows, scans, and variational autoencoders. And a lot of these yellow blocks right here will involve GNNs, which are graph neural networks. And I guess the raison d'etre of graph neural networks are because you've got a different number of nodes. So if you had a typical neural network, like a feed-forward neural network, you're dealing with fixed length inputs, so fixed data dimensions. But a GNN has, I guess, some kind of pooling operation. Correct me if I'm wrong, that allows it to deal with different shaped graphs. Is that Peter? Is that the point of GNNs?
Yeah, GNNs they use what's called like a message passing algorithm. Actually, I guess in terms of answering your questions, they're kind of like transformers. Like whatever input you put in is the same input you get out. And the reason being that they use like message passing to like aggregate information across the graph, which only looks at like the local neighborhood. So for example, if you have a node that's connected to another 3 nodes, and those 3 nodes have another 3 nodes they're connected to each, that initial node is only going to see those first 3 when it does message passing. And that's what allows you to like process information about the graph without having to change the size of the graph and keep it the same size.
Okay,
It's a
so
poor
it's going to be a
explanation of it,
degree,
but
like a degree per layer of this message passing graph neural network, and like the information moves each layer 1 degree of the adjacency matrix.
each
Okay.
each layer uses the adjacency matrix and aggregates information from what determined the graph neural network literature is 1 hop away, which means any node's direct neighbor, so an edge is directly connecting it. But if you keep applying, if you have more than 1 GNN layer or 1 message passing layer, you're going to see farther and farther away, because with 1 layer you see 1 hop away. With 2 layers you'd see 2 hops away, because your neighbors that you're looking at again will have seen their neighbors, and so on. And so that's how you can get information about the whole graph, by just having a deep graph neural network. There are some, just stop me if you want to keep going, but like there are some downsides to this approach. The main one is that the representations of nodes that are calculated if you have a deep graph neural network are over smoothed, because you're seeing like basically this approach would lead, if you had enough layers, would lead to every single node having the same representation, because you're just aggregating information across the whole graph.
Okay. So there's like some kind of averaging or over smoothing effect.
Yeah, it's called an aggregation step, and they can use you can use max, you can use anything that can like take a sequence of vectors and spit out a single vector. And
so here's an example
of
like this kind of GNN being used in this context of diffusion models and graphs. So let's just go straight into one of these models that are referenced or cited in this paper. So it's called EDP GNN, and it's the very first score matching based diffusion method for undirected graph generation. Okay, so through modeling symmetric adjacency matrices regarding the different scales of noise added to the upper triangular segment within the neural network. Okay, so it's adding noise to adjacency matrices, and because they are undirected, it's a symmetric adjacency matrix because an edge is bidirectional. So given that it's adding noise, Gaussian noise, that's a continuous random variable. So it's like corrupting these discrete 0, 1 edges with a continuous random variable. So, okay, so that's kind of sidestepping this discrete nature of graphs and like just representing them as continuous. So let's look here. So graph neural networks map graphs to vector representations, as you said, natural models for graph structured data, and the message passing mechanism guarantees that the output representation of an input adjacency matrix is equivariant to permutations of the node or ring pi. Now that's important. That's another kind of challenge in graph neural networks, because if you had, for example, a graph of 3 nodes, like a triangular graph, then there are 6 possible orderings of those nodes in some kind of index space, which would generate your adjacency matrix. And the adjacency matrix is invariant to that node ordering. So it looks the same no matter what order you place these nodes in your array. And so that's a problem, because when you're...
So wouldn't the adjacency matrix not be exactly identical, but rather a permutation of the rows or something?
Oh yeah, that's the point, right? Okay, so it wouldn't be exactly identical, so it's difficult to compare, but they would represent the same graph.
Exactly, yeah.
So they should have the same probability in the model.
Yeah.
And so you want to try and achieve this kind of invariance. So that's one of the main challenges. Here is like a relatively early paper that discusses this like right at the forefront. And so it's like you've got an ordering of nodes pi with an adjacency matrix A pi. And in order to achieve this invariance, they are going to be using some kind of like pre-prescribed node ordering. And that is in order to evaluate this kind of computation. So one adjacency matrix compared to another adjacency matrix. And so permutation invariance is desirable since the true distribution is inherently permutation invariant. And so what they're able to do in this paper is show that by using a permutation equivariant score function, the corresponding distribution is permutation invariant. Okay. So this is about using a specific neural network for this score function, which means that the corresponding distribution is permutation invariant, which is this desirable property of the model. Okay. So that's one example. Is this kind of graph generation? Well, what was the goal of this in order to? Yeah, I mean it's generating these adjacency matrices. And I guess the idea is that by starting from a continuous random variable, these random variables will come close to 1 or 0, depending if the edge is there or not. And so that's one way around the discrete nature of graphs. And you'll find this is a common theme with a lot of these models and applications. Either the model sidesteps the discrete nature of graphs, or the application isn't really graphical in nature. The application has been reframed so that the representation, say, of the molecule is in a continuous state space rather than a discrete kind of adjacency matrix. So at this point, we can have a look at, we can compare if that's the same as kind of what's already been done in the literature, because this review paper gives a review of existing methods apart from diffusion models. So we can have a look at variational autoencoders, for example. Here is a classic paper on variational graph autoencoders, and this does actually deal with the discrete nature of graphs quite nicely, because the decoder involves an inner product between continuous random variables pushed through a sigmoid function, which describes the probability of the edge existing. And so this training objective is a variational lower bound of the likelihood of this adjacency matrix. And by using the Jensen's inequality and a variational posterior distribution of this latent variable, which is an encoder, then you can optimize this bound of the probability of the adjacency matrix via stochastic gradient descent through Monte Carlo samples of this expectation. And yeah.
Go ahead. I'll say after.
And end up learning a representation of the nodes, because there's a latent variable per node, and this is operating on one big graph, not many small graphs. This is a citation network, and the edges represent connections between nodes, and each node is a document, and the color, which is not given to the training data, is a document class. And so it's basically an image showing that the latent variable is useful in clustering some document classes together. Peter, did you want to enter?
Yeah. So this was I think is a really good paper, but I think it illustrates an aspect of research, which is that when we introduce new problems, even like the authors of this paper are some of the most successful researchers in the field, and they missed something, which is in part because they probably didn't have to deal with it in the application that they applied it. So see how they're calculating edges based on the inner product of two node representations.
Mm-hmm.
That this model by definition will always if two nodes have the same feature string and then the model says for one of them that they're going to be connected to another node, then the other one will also. So like if you have two carbon atoms in a molecule and the model says this carbon atom is going to be connected to the nitrogen atom, then it will automatically say that the other carbon atom is going to be connected to the nitrogen atom. So
because they have the same latent variable.
Yeah, because they have the same latent variable. So one interesting failure case of this model is that it will produce like basically like very almost, I think it's like almost symmetric graphs, because any node that if you have common node features between two nodes, it will always connect them to the same other nodes that it says they should be connected to. So it doesn't deal with the case where you have like recurring node types and then also but asymmetric graphs with respect to that. There's a lot of other recent papers that have been dealing with that though. We actually covered one a couple weeks ago. That's why I know.
So that's a really good point about like the application area really constricting the type of method you can use, which seems to be a common theme in graph neural network literature.
For me, it's actually what I find is that there's a lot of there's actually the public data sets available for doing research on graphs are somewhat limited with respect to the actual number of applications that these can be applied to. I've even heard one researcher I talked to said like anything can be modeled as a graph. So in theory, you could create a data set about anything with graph, but it's like molecule data, citation networks, knowledge graphs, and some abstract syntax trees and code. So basically, there's maybe like 5 public data sets available for doing this type of research. And the ones that have been used so far often have these like the specific structure that's not shared amongst them all. But because the researchers only applied their method to that domain, they didn't create a method which generalizes past it. So to me, it almost suggests that. Oh, sorry.
It's interesting the researcher said that anything can be modeled by graphs. Well, yeah, that might be true. I can think of some more examples that you didn't mention, such as like recommendation systems. There is one here. Here's like an example of a nice diagram of a recommendation system where you've got users using some platform. Say it is YouTube, and they're watching videos, which are these items. And so if you watch a video, there's an edge connection. And between the videos, there's connections because the videos are related and maybe linking to one another. And there are some demographic connections that the recommender system wants to identify to recommend similar videos as someone else who's watched similar videos to you. Or this could be an Amazon shopping website where you want to advertise similar products to what other people with similar demographics have bought, something like that. So yeah, a lot of things can be modeled as graphs. However, some of these applications in this paper, like molecule conformation generation, aim to use a representation that isn't a graph. Even though a graph representation might be quite natural, they're not using that because it's just easier to do machine learning on continuous variables. For example, a molecule can be represented by a 3-dimensional geometry or conformation, which atoms can be noted as the Cartesian coordinates. Well, those are continuous, but those are kind of difficult to deal with because the Cartesian coordinates of the molecule can be shifted and it's the same molecule. The molecule can be rotated and it's the same molecule. And so as a result, several techniques use intermediary geometric variables that also have roto-translational invariants, such as torsion angles, bond angles, atomic distances. So those are the angles between the planes that are formed by these bonds, for example, and atomic distances between atoms to avoid forthrightly modeling atomic coordinates. But since these are
one thing I wasn't a big fan of in terms of these applications is one, I feel like there's a lot more applications. So I think it might have been better not to focus on these two. And then both of these applications talk almost exclusively about the 3D structure of molecules, where the 2D structure of molecules, like knowledge of the 2D structure of molecules is like a necessary but not sufficient condition for knowing the 3D structure of molecules. So they're actually like the review is on graph generation, but all these applications are actually a completely not a related but not the same problem. Like you couldn't apply any of these methods as they are to the problem that they're talking about in these applications because they don't have the ability to generate 3D structure. So I was like, why do they have such a long application section on something that's not related to, that's not the problem of graph generation?
Yeah, so I would agree that virtually, well, there's some of these methods that are based around autoregressive generation of graphs, but those are few in comparison to these kind of 3D conformation and like 3D structure generation, which encompasses kind of most of these examples in these application papers.
Yeah, because like one interesting thing is that for protein 3D structure, AlphaFold models the graph as a complete graph, and then has these latent edge representations of each edge in this complete graph. So, for example, AlphaFold, which is like the state of the art in generating 3D, like the tertiary structure of proteins, it completely bypasses the problem of graph structure generation. So, yeah, I was like, why? Yeah, I felt like it wasn't the right thing to look at for applications of graph generation.
And why do you think graph generation is so difficult? One problem is, well, GNNs representing they require the adjacency matrix as an input, but for large graphs, the adjacency matrix requires like n squared memory, which turns out to be infeasible over like maybe 40,000, 50, 100,000, a million nodes for GPUs, single GPUs. So is that but that is one difficulty, but there must be more kind of fundamental challenges involved in generating graphs. Do you know of any of these? I mean, one of them is the permutation invariance problem of comparing different graphs. And another one is they're not as structured as, say, images, and they're discrete. Would you say that's a good summary of the problems that are involved in generating graphs?
Well, I also like, because they have in the beginning section that list of the maybe four different problems, and one of them is like the complex. Yeah, it says complex intrinsic dependencies. So I think that's like one of the fundamental problems, which is that there's like with images, you know that you're generating a grid, but with graphs, there's like a valid set of dependencies for each graph, which are for a distribution of our graphs. And learning that, I think, is pretty complicated. because they're related to each other, you know. Like you can't make one edge connection in independently of all the other ones usually.
Maybe we can think of that as through an example. So unlike image data, the nodes aren't independent, identically distributed. So an example, well, actually the nodes on an image, it depends what you think about as a node. Anyway, an example I can think of like is a citation network, and a topic of journal papers conditioned on the citation network, and the titles of the papers are not independent. So the topic will be correlated with the papers it references and the papers that it cites. Is that the kind of complex intrinsic dependency that it's talking about, or is it more talking about the edges must be directed in the case of the citation network, because one article can cite another, but it doesn't need to be referenced by it?
To me, it's more the former. That like an example that I think of is more is that a carbon atom can have at most 4 bonds, and so but it can also have 2 bonds and 2 free electrons. Like there's a lot of different ways that you could do it, and so if you have like a carbon atom that has 2 bonds on it and you're trying to generate the graph, you could either say, okay, I'll leave it as it is, or I'll add another 2 bonds to it. There's a lot more to this. I'm going to give a poor explanation, so I'm going to stop talking.
Okay. Yeah, but that's a nice clarification of what this means, because I don't think it's actually clear in this paper, but now it's a bit more clear. So that's a good example. So essentially what we're saying is possibly that none of these methods by themselves deal with these problems, which is why they're open questions, which is possibly why we're quite constrained by the task and the data set. And maybe that's why there aren't that many data sets that exist that these kind of methods can be applied to. So looking at the future challenges and opportunities, there are increasing efforts to develop diffusion models and graphs. Well, that's actually clear because there's a lot of papers in the past 2 years. The most exciting diffusion models for images are developed in continuous space, but in contrast to discrete nature graphs, yet hardly possible to deploy diffusion models on them. In this case, several works have tried to make diffusion models suitable by introducing discrete probabilistic distributions like categorical distributions, or bridging the gap between continuous and discrete. So I am modeling these kind of discrete random variables as continuous, which is the first paper that we looked at. And so there's just a lack of universal and well-recognized method to solve this problem. So it really depends on what kind of problem you really want to tackle in the method you're going to use. Are you using that kind of variational autoencoder method? Yeah, it might be relevant if your node embeddings are known to be different for each node, but if they're the same, then you might run into that issue you mentioned. And if you can sidestep the graph entirely and use continuous random variables, then maybe you should. And incorporating conditions into generative models is critical to guide desired generation. For instance, instead of generating new random samples, conditional GAN and its variants with auxiliary knowledge have achieved remarkable success in controlling image generation. Okay, but in the graph domain, to generate molecules and proteins with specified properties, it is significant to set certain constraints on the design of graph generative models. Okay, so introducing extra information as conditions into graph diffusion models is a research direction. But this seems like this kind of conditional generation is dependent on being able to generate molecules. So Is there a paper in this which is particularly good at generating monocules, which are valid? That kind of problem might need to be solved before you go into conditioning on data like, I want a monocule that is soluble.
I have a question. Why is the discrete nature of like graph data such a bad problem with diffusion models?
Because diffusion models operate in on processes.
But numerically discretize them, right?
Numerically, in what way?
I mean, you have to use some sort of numerical discretization scheme to work with any of these like stochastic processes.
Yeah. So for example, that could be discretizing in time, going from a continuous process to a discrete process. But that you bring up a good point in that there are different ways of discretizing problems. But that doesn't mean, so discretizing the number of the continuous time to discrete number of time steps or layers of this kind of continuous VIE picture is different because we're still working in continuous state spaces. So the state spaces are, for example, the image state space is the pixels, and it has dimensions number of pixels. And so they're all continuous random variables. Whereas edges in an adjacency matrix are discrete random variables, and you can relax these continuous random variables and model them as continuous.
Yeah, that makes sense.
But I think like looking at why you would need to discretize in time, because time is these kind of models are Markov, and so then you need to step through time. And so this discretization is like discretizing like an index space, and it's not a state space. So the time is like an index space the same way as like an image has an index space of 2 dimensions, which is like the frame of the camera. But really the pixels are continuous random variables, right? Because they have a color. Even then, like you could argue that they are discretized because it goes from 0 to 255 in brightness, but their model is continuous. I think it's the difference between like an index space and a state space.
So I think that the discrete, like I don't know anything about diffusion models. I do hope to read some papers soon where I can learn. Well, I don't know them well enough to understand the math. Put it that way. But the discreteness of the reason why I think it's a problem is because like with images, for example, we've kind of mentioned that you can model these as a graph because they're basically a 2D grid which can be modeled as a graph. But you know that graph structure. Whereas with graphs, you don't know that graph structure. And so when you're generating it, you have to generate that graph structure, and which means you have to say which nodes are connected to which nodes. And so if you have n nodes, you have n squared possible links. Now, if you want to back propagate through that, you can only back propagate through positive examples unless you generate negative examples, because there's not like, well, maybe you could, I don't know. It's making me think about something. But anyway, to me, the discreteness, the real problem is that it's, well, there's 2 problems. One, it's very sparse in terms of like most real world graph data has really sparse adjacency matrices. So you might have like 10 edges in the graph and 100 possible edges. And if you have 1,000 nodes, then you'll have 1,000,000 possible edges and maybe only 1,000 edges in the actual graph or something, you know? So this creates like a highly imbalanced problem where you have to figure out how to deal with that. And then also the discreteness is irregular. It's not like a pattern that's super obvious where like in images, every node that's right, every pixel that's next to each other will be connected. But for me, I think it's more
also like constrained, like it can be constrained by the number of, you said, number of carbon atoms connected to other atoms. So it can, it's like, it could be a constrained space as well.
Yeah, but yeah, exactly. But yeah, for me, with these approaches of generating the adjacency matrix, the hardest part is the sparsity of the matrix as the graph grows larger. And that's what I think would be the most challenging part of extending these methods to larger graphs. Because if you have, like I said, if you have 1,000 nodes in your graph, then you're going to have 1,000,000 possible edges, but you're probably going to have like many less, like 1% connectivity or something. Which is still 10,000 edges. So anyway, that creates a really hard problem for a model to learn to be able to do, to generate edges for.
I think that's a good place to bring it to a close, unless anyone has any more kind of questions or discussion. Be happy to keep going.
Yeah, so I have a question. So if you keep the graph structure fixed, for example, so that means generation on, let's say, edges or nodes. If you want to generate, I don't know, you have the structure of a molecule and you want to generate sort of like what molecule is it going to be, things like that. So that's much easier than trying to sort of generate an adjacency matrix, basically, right?
I think so. I think there's an example of that in one of these papers. And if you bear with me, I'll try and find where they might have fixed the number of nodes.
Then for that problem where you know the adjacency matrix, can you just take like all the diffusion methods applied to images and apply it to graphs then? Because you know the structure, which is the same as in images.
Yeah. Hang on though, if you know the adjacency matrix, I think you'd have to fix that adjacency matrix, yeah, because you also have that problem of there's n factorial adjacency matrices which describe the same graph. So maybe you have that that problem still. So this one is generating graphs kind of step by step on adjacency matrix by a recurrent neural network. That one's different. Yeah, there's one of these papers which fixes the structure somehow and then uses diffusion more directly. I don't think it's this one, but it could be. So I think the answer is basically yes. I mean, that's what you're talking about, right? So here you have a single state space, which is the angles or like the torsion angles between planes of the bonds. And so you start with some kind of random distribution and diffusing towards the data distribution. But here, the adjacency matrix is fixed, but it's not what you're diffusing over. It's actually used to in the like graph neural network that produces the score, which is the gradient of the data distribution in the direction of, like, it points in the direction of the noise you've added of this continuous state space, which is the torsion angles. So here it's like really nothing to do with the graph anymore. It's more to do with what are the values of these angles given this adjacency matrix. and node embeddings. So I think, yeah, you've then fixed the adjacency matrix, but you're not really operating on graphs. So this kind of application is certainly possible.
Do they use the graph structure, or do they sort of encode the graph structure somehow? Like, do they use a GNN?
Yeah, let's see. So it would be in the model, the score model. So graph field network, which takes in this G, which is, I'm guessing, adjacency matrix. Yeah, is vertices and edges. So this network takes in, is basically a GNN or something similar, but it's roto-translational invariant because of these torsion angles need to be modeled that way. And it's going to take this edge information and vertex information as an input, but output continuous variables. Okay.
Cool. If no one has any more questions, thanks, Ben, for presenting this overview. It's really cool to see it does seem like diffusion is state of the art in graph generation right now. So we'll have to see where the field progresses.
Well, I don't know, is it? There's a lot of papers, but what are the results? We should have a look at the results of these papers. And also the types of problems, like maybe you can't really class this as generating graphs, but more kind of, here is a problem that involves graphs as a representation, but we're going to take a continuous representation and use those variables and find what the distribution of those variables are, conditioned on the adjacency matrix. Maybe that's kind of a nice application of the diffusion model. But yeah, okay. Thanks for listening, everyone. I hope you learned something.
Thanks, Ben.
Thanks a lot.